I don't see anything on my monitor at all. I don't see that.
Okay.
I don't know if it matters to you, but I can't see any what you're.
Okay.
You,
I called the text.
I mean, I don't need to see myself as long as you're getting a video.
We are.
Okay, perfect. Thanks. Same thing as usual. Some on the board, some talking, a lot of walking. Okay, because we are good to go today. I can't see myself, so hopefully we're good to go. I have a couple of questions I'm going to answer that I got on the web, on Canvas. Don't really have any announcements here. We are now coming to week 3. So there we are here on week 3. The week 3's video module is already there. It's about the same length as the other 2. And if you've watched the first 2, we're getting more and more focused on scheduling type problems. And we continue that with this third video module. I also assigned case study 2. So if you haven't looked at that, that's based primarily on the material that is in that third video module, a little bit that we're going to do in class. So do have a look at that, and it's due on the 18th. So you got a couple of weeks to do that. Let's see. I guess I will go through the questions, and then we can decide, or I'll see if you guys have any more questions. So I got a couple of questions about file downloads from the website where I store the video modules. I fixed that. There was a security problem. I had something wrong in the links that I had, but it should now be fixed. So if anyone can't download files, please let me know. I think I'm pretty sure that's fixed. I also put the files on Canvas also, so they're in both places. So a couple of interesting questions, or a few interesting questions here. This one says, in video 1, I was wondering if it's possible to create only one table with all the information, or it has to be done with 2 separate tables. So this has to do with the, let me go back and grab the Job Shop 1 model, the baseline model that we did. And so in this case, we have 3 different part types, and they all have different processing sequences and processing times. And we define that using 2 tables. We have the parts table, where we have a part column, which is a key column, and then we have a mix column. And then we have the sequence table, which is a relational table. So by relational, what that means is that it has a foreign key that's defined in the parts table. Okay, so it's that primary key, foreign key relationship. And so what that does is we can look at the parts, and then we can, you can think of it as filtering the sequence table based on what type of part it is. Okay, so we have 2 tables. One defined parts, one defined the sequence, and they're related. And so we use that in the source. So we have we are creating entities based on a random and arrival time, and we're creating a table row reference to the parts table using the mix column in the random row. And so since those values are all 1, that means they're all going to be equally likely. Okay, so the question was, can we do this with 1 table? And I'm going to give kind of 2 related answers. First, I don't know any way to do it with 1 table. You could do it with 4 tables if for whatever reason you don't like the fact that the tables are related. You could do it with 4 tables. You would have to have a separate sequence table for each part type. Okay, and then so if you did that, so instead of having 1 sequence table that has everything, I could have 3 different sequence tables, and then back in the facility view, I could set the sequence right here on initial sequence. So if I did that, then I would still have a parts table because I have to be able to generate the parts randomly. And I would have 3 different sequence tables, but there wouldn't be the table relationship. Okay? I don't know why you would want to do that, because the related table seems a little bit clearer to me. And more importantly, we're going to see this becoming more and more important as we get further into scheduling applications, because we look at this model, This is a really simple model, right? So I have parts and I have the sequence. But you can think about each one of those sequences, right? So if I look at that one, the top one there where I say input at S1, that corresponds to part 1 being processed at S1. In a general scheduling context, we can have things like secondary resources. So maybe I have operator requirements. I have raw material requirements, right? So for each one of those operations, I have additional requirements, potentially. And what we're going to see is we define those relationships using additional tables. And they all have this same primary key, foreign key relationship. And so what you'll see as we get further, we're going to have not just 2 tables, but we're going to have like 10 tables that are all going to have this primary key, foreign key relationship. So having an understanding of that type of table structure is really important. Okay? I also got a couple questions that I didn't put on the slide because I forgot one and then I got one later. When we switch from doing random arrivals somewhere down here when we used an arrival table, right here, right? So we switched the model somewhere down here in the arrival table. In the video, I guess I didn't show the part where I got rid of this table row reference, right? And so if you look back to the baseline model that I copied, right, my baseline model that I copied, I manually set the table row reference using random row. And then I copied this model down here. And then I said, okay, I'm going to change the mode to arrival mode. But in the video, I guess I didn't show where we got rid of this table row referencing. And so if you do that, if you have 2 table row references, you'll get an error. Because Simio doesn't know. You're trying to set a reference to the same table. And you're trying to do it at the exact same location in simulated time. Because it's set to do before creating entities here, so that in that model, we can use the table part type to define the part type. So it has to be done before it's created. But we're also creating one before we're creating a table or setting a table row reference before it's created when we do an arrival table. So if you try to do that, you'll get an error. So sorry about that. That was an omission on my part for not having that, for including that detail. Okay? Anyone have any other questions about this particular question here, about this 2 tables? And we're going to see this over and over and over. So understanding this how related tables work is going to be critical from here on out. Okay. I got a question about OpQuest and the ranking and selection procedure. So I'm not going to read all this to you. I'll let you have a look at it. It's also on Canvas in the discussion forum. And I will just say that in the video, I didn't spend a huge amount of time talking about this process. I didn't talk about OpQuest too much, and we didn't even use the ranking and selection. So let me just spend a couple of seconds talking about that. And so that's really what this focuses on is OpQuest and the parameter settings for OpQuest, and then select best from KN. And before I talk about it in general, let me just show that all of that is discussed here in Chapter 9. If you go look in Chapter 9, it talks about using OpQuest and then using subset selection and then using the ranking and selection procedure to try to find the optimal solution. So there is a process you go through, and it's talked about in detail here in Chapter 9. But let me just give a really, really, really brief overview of how that works here. So I want to do one that I did in the video. Here it is, basically the one. And the one that was that I used OpQuest on was this max throughput. Okay, and so the question had to do with the parameter settings here. So if we look at my mean arrival time, I have the min value of 9.3 and a max value of 10. Okay, and so then I have a step value of 0.05. And the question was, setting those is important. All 3 of those things is important, right? Because if I have my minimum value, say, above the true optimal, I'll never find the true optimal. Similarly, if I have my maximum value below the true optimal, I'll also never find my true optimal. And if I make this step size too big, then I could also potentially not find you're not going to find the guaranteed true optimal anyway, but the practical true optimal. Yeah.
Is there any significant difference in using, doing this for the L value? We set a maximum acceptable value. What would happen if we use the constraints instead? Is there any difference?
When you use the constraints, no, it's not going to be different. You typically don't use constraints on an input value, because we're only doing the parameter changing there, you typically use the constraint on a computed value, right? And we're going to have an expression where we do the constraints, but the net performance is not going to be any different. The net behavior is not going to be any different. Okay, so let me just step back a second and talk about this particular example. Is not a great example of using OpQuest. It's just not a great example because there's only one parameter. The values are small, right? The range that we're interested in is pretty small. And so it's really easy to just numerically evaluate all the interesting alternatives. In the general case, though, you usually have a lot of different controls. And so the solution space is humongous. And so the idea of using OpQuest is the OpQuest can find its way through the solution space and find you good solutions. If you have a problem like this where the solution space isn't big at all, I mean, I generally wouldn't use OpQuest for a problem like this that has a single variable. You know, I would just do some screening and try to figure out what those close values are and kind of expand the screening. So a little sloppy on my part for using OpQuest here. Okay, so what OpQuest does when you tell it, when you set up the parameters, you know, you say, I want to include these variables, and then you give it some general parameters for the experiment. Experiment parameters here, like minimum number of replications, maximum number of replications, maximum number of scenarios, and so on. You give it that, and OpQuest just goes through and sets the parameter values and tries to find the good solution. Okay, and so what you see here is the result of an OpQuest run. And so the red values don't meet the constraint, because this one I was doing a constrained optimization where I was saying I want the maximum throughput value subject to the constraint that the average L be less than 50. Okay, so these values that are in red don't meet that constraint. All of the other ones that don't have red do meet that constraint. Okay. So I sorted these based on throughput, and so this is the one we would look at and say, well, this has the highest value, right? So 9.7 and the throughput value of 6.183. I think that's what I ended up with in the video or something. Okay? Now, there's a lot more that I kind of skipped here. Well, I just didn't do it. If you look at these values, so if I look at these checked values right here, and I look at the response results, and I look at the throughput response here, oops, that's number completed. I need my throughput response right there. So I have a lot of values that are almost certainly not statistically different, right? So if you look, these values, this is the mean value here, and then the beige box is the confidence interval around that mean. And so when I look at my highest values, maybe that number 8, number 5, and number 6, and number 10 here, these guys, and probably even 50, probably all of them, they're just not statistically different. So when you say, okay, the best one is that one on the far left that OpQuest identified by just looking at this sample mean right here, that's almost certainly it's certainly not provable that that's the true best of these scenarios because the confidence intervals are so wide. Okay, so OpQuest doesn't go through and find the statistically best result. That's where these other procedures come into play. Right, so if you look at these, and this isn't a good example because it's not a really difficult problem, but if I look at my throughput value and then use subset selection, what subset selection does is it divides the scenarios. I have how many scenarios here? I can't count. They're not in numerical order, so I don't know, 20 or so. It divides them into two groups, right? The loser group and the potentially best group. So all I really care about are those that are in the potentially best group. Okay, and of those ones that are in the potentially best group, a couple of them are not feasible because that subset selection only considers one performance metric. Okay, so what I'm really interested in are all of those ones that are in the light brown or beige or whatever color that is that aren't red. So that would be all of the ones that are checked in the OpQuest run. Okay, so if I really wanted to know the true best amongst those, that's where select best from KN or the GS come into play. And so we have these other two add-ins, select best scenario using GSP and select best scenario using KN, both do basically the same thing. They take the scenarios that you give them and then it tries to identify the statistically best one. Okay, so it runs additional replications and it performs statistical comparison tests, and it will either end with one scenario chosen as best, and it would be statistically the best, or multiple scenarios that it can't differentiate between after it's exhausted the computational method that you've told it. Okay, and so that general process that you follow to find true optimal or the true best would be use OpQuest to take your big solution space and narrow it down to some attractive scenarios. Then take subset selection to partition those attractive scenarios into the losers and the potentially best, and then use one of the ranking and selection procedures to try to find the true optimal. Okay, and that's what talked about in chapter 9 that I didn't talk about here. Okay. Let's see. Any other questions about that? I think that's all the questions I got. Yes. Any other questions for me? Those are all the questions I got on Canvas. I got a whole bunch more questions, but most of them I chose to just answer on Canvas. So if you're not looking at the discussion forum on Canvas, you should be looking. People ask questions and all, and there are a lot of questions I just answer there. And I pick out the ones that I think would be of more general interest here to talk about in class.
Yes. Not so much a question as like a comment, but hopefully you can give me some assurance. Like going through the third video module and like following along, that kind of thing. It's super easy to get lost and like not like find your way back to like a good spot where you're like, oh yeah, this is the next thing to do or whatever. Just in all like the tables and connections and that kind of thing. Mm-hmm. Is that expected or is it like do I just need more practice or what?
I'm not sure exactly what you mean by it's super easy to get lost in. You're trying to follow along with the video.
I'm trying to build along, and it's like if I click the wrong tab or the wrong thing, or like I can't imagine myself remembering how to like set up the same thing in a different problem context.
Yeah. So the videos are pretty dense in terms of the amount of information. And so to do these effectively, if you're not familiar with this, you're going to have to go through and stop the video and try something, stop the video and try something, stop the video and try something. Yeah, I don't expect you to be able to watch it one time through, replicate everything, and then be able to do it again on command. It's more than that. But what I do need from you is feedback on what you find. You know, if you find things super confusing, tell me, and I will spend more time talking about those. And like this whole notion of table relations, it's critically important. So I don't mind spending more time on it. And any other things like that are confusing, bring those up, and I'd be happy to spend time. But yeah, it is confusing when you look at. We've talked about in the beginning of the class, if I look here and I have the tabs across here, I have all of my objects over here. So they all have properties and they all have data and they all have processes. And so, yeah, it's pretty easy to clicking around to.
I think my main point of confusion was when things are defined in tables and when you have to go back to the actual facility layout and then set properties.
Yeah.
I was like,
Yeah. That will get easier as you practice. But it is information dense here, the ones that I'm doing here. Okay, anything else? Yeah.
I almost completely about choosing the properties for table values.
Okay.
For example, sometimes we use object reference property, element reference property, and only properties sometimes. And for example, in the first video, I guess, we define some value, for example, expression, and then also it works when we copied object values there. Mm-hmm. Sometimes we can use interchangeable, I guess, but sometimes I cannot find.
Yeah, it depends on what you want. So if you look at this example here, let's see, drop shop 1, and I look at this mean inner arrival times control, go back to my model, my data. Sequence. So this is defined as an expression property. And so an expression property can be any combination of numbers, functions, random variate calls, and so on. So any combination of those. If we define it as a number, then it's just a number. Okay, so I think in some of the later videos, particularly in video module 3, I don't use random processing time expressions. I use specific numbers. Okay, and so if you have an expression, I can paste specific numbers into an expression because a number is an expression, but not the other way around. So if I say that this number is real or integer, I can't say random.normal or random.exponential because that's an expression. And the difference is that if you have an expression, it gets evaluated every time it's called. So you can think about when I have 10 entities in a row that go to a server, and it always calls that, I'm sampling from that random distribution 10 different times. If I just have a single number there, I'm using the exact same number every time. Sometimes I want one, sometimes I want the other. Okay? Anything else? Okay, so I'm going to pick up and talk a little bit more about scheduling here. Kind of ended up really flying through schedule generation. But basically, we were talking about this notion of a simple job shop problem. And a job shop problem is characterized by having different entity types that can essentially have random flows through the system. If you look at the classical job shop problem in the OR literature, they're saying, I've got X machines, and every part visits every machine just in a different sequence. That's not our definition. We're just saying the sequences can be anything. You have arbitrary sequences. It doesn't have to be every part visits every machine, but it's just this notion that you have arbitrary sequences. Talked about Gantt charts and how they represent the sequence. Go through disjunctive graph representation, and then this whole mathematical formulation. And with this mathematical formulation, with different solution methodologies, relatively small problems, I can get provably optimal solutions based on make span objectives and things like that. And then I talked about schedule generation, this is the part that I flew through at the end, and basically said, here's what we're going to do. We're going to talk about this basic algorithm where we're creating the Gantt chart by this simple list method. So I have a list U of unscheduled tasks. I have a list P of precedence feasible tasks from U, so the unscheduled precedence feasible tasks. And from those, I select a task set S, which meets some criteria. And from S, I pick a task and schedule it. I just do that sequentially. And what I did at the very end was solve this problem using schedule generation. Okay? So if anyone wants to see it, I'm happy to do that again. Hopefully you guys tried it. I'm going to do a slightly different example here in just a second. But does anyone want to see that process? Okay, I will again say schedule generation is really important. So make sure you understand how it works, why it works, because as you'll see when we get to discrete event simulation, it works in the same basic methodology. Okay? So I want to revisit this notion of active and non-delay schedules. As part of when I was reviewing the video last time from last class, my coverage of active schedules was just pretty weak, frankly. So I thought I would spend just a little bit more time talking about this notion of active or non-delay schedules. So what I did was I went to a pretty classic book on scheduling and pulled out this example. And so from that example, or that is an example, but I can have these two definitions that we're interested in. The first definition is a non-delay schedule. Formal definition says no machine is kept idle when there's an operation available for processing. Okay? Active schedule says no operation can be completed earlier by altering the processing sequences on machines and not delaying any other operation. Okay? The schedule that you see right there is active, but it's not non-delay, right? Because if you look right here at time 1, right there at time 1, operation 1 on machine 1 is done at time 1, and it can immediately start on machine 2. Okay, so that little time block right here. So there's a 1 time unit block right here that violates this rule. Okay? But it is an active schedule because I can't, if I move 1 over to here so that it finishes earlier, 2 is going to finish later. Okay? Does that make sense? So a non-delay schedule basically says if I can do something, I'm going to do it. An active schedule is a little bit different. An active schedule basically says I can't move something earlier in the schedule without it causing something else to be later. It's not exactly what it says, but for our interest, that's close enough. Okay? All right, so let's look at this with our schedule generation. Okay, so here's what I said I was going to do a little bit of schedule generation here. We're going to do this problem. So I have this problem here, and let me write this down. So I have part 1, and I'm going to say that it goes to machine 1, and it takes 1 time unit. So I'm going to use the same syntax that I did last time. Then it goes to machine 2 for 3 time units. So that's what's defined somewhere down in there. Then I have part 2, which goes machine 3 for 2 time units, and then it goes to machine 2 for 3 time units. Okay, so the sequence basically says I have part 1 goes from 1 to 2, part 2 goes from 3 to 2. Okay, and that's what you see there. And what I'm going to refer to these as, because I need the operations, I'm going to call this part 1 operation 1, part 1 operation 2, part 2 operation 1, part 2 operation 2. So I'm going to call this because I need to differentiate between those. Okay, so if I think about doing schedule generation, and I'm not going to do the entire schedule generation, I'm going to start from a particular space. I'm going to start here, and so here's M1, here's M2, here's M3. I've already done 1, 1 time unit, and 2, 1, 2 time unit. So that's already in my schedule. I've already scheduled the first 2 operations. Okay, and so now what I have is I have my unscheduled tasks, which are 1, 2, and 2, 2. Really simple problem. 2 parts, 2 processes each. I've already got 2 of them scheduled. I only have 2 left. Okay, so now in the schedule generation context, the next thing I would do is I would say, okay, well, let's create the set of precedence feasible tasks. Okay, well, they're both precedence feasible because I've already scheduled the first operation of both. So this is 1, 2, 2, 2. Okay, now here's where I'm going to take a slight modification to the schedule generation that I did my algorithm. In the algorithm, what I said was we're going to set the start time, T, to be the minimum start time, right? And the thing I left you guys with last Tuesday was to think about that rule. Okay, well, so now we're gonna expand that a little bit. Okay, and I'm gonna think about the 2 basic rules that people use with schedule generation. The first one says I'm going to compute the minimum start time for each of the operations in S, exactly what we did before, but I'm also going to compute the minimum completion time. Okay, so if I do that and I say here's, let's see, 1, 2, and 2, 2. Those are my 2 operations. And let's do min start. Right? So the minimum start for 1, 2, it can start immediately when this one's finished, so it can start at time 1. Right? And when I look at this one, 2, 2, well, it can start here because there's nothing on machine 2, so it can start at 2. And so now when I have the min value, it's 1. Right, and so the rule says, okay, I'm going to take everything in P that has a starting time less than or equal to that value, and that's going to be my set of schedulable tasks. So S here would be 1, 2, and 1, 2 only. Okay? Because my cutoff time is 1, and 2 can't start until 2, so it can't start, so it's not in my schedulable set. Now, if I do the second one and say this is the min finish, okay, so the minimum finish for 1, 2 means it starts right here at time 1, takes 3 time units, right, 3 time units, so it finishes at time 4. If I look at operation 2, it starts here on 2, it takes 3 time units, so it's 5. Okay, so the minimum now is 4. And so S in this case says, give me all the operations in P whose start time is less than or equal to 4. Okay, well, it's both of them. Right, so it's 1, 2, and 2, 2. Right, it's both of them. They both meet that criteria. Okay? Does that make sense? Yeah.
Could you please repeat the criterion for the second set?
The criterion for the second one is I'm going to compute, what I'm trying to compute is my cutoff time. Right, so we have T, which is my cutoff time. And the basic schedule generation rule says once I compute my cutoff time, everything that starts prior to the cutoff time gets included in S. So for this column, my cutoff time is my minimum start. For this one, it's the minimum finish. But once I compute that value, that cutoff time, I use the start time to decide which ones go in S. So even though I computed cutoff time using the finish time, I use the start time to decide what gets promoted from task P, from set P to set S. Okay? So let's think about this. So let's start with this one, right? So if we were using this rule, and we did schedule generation, we would then say, okay, well, I only have one feasible task. It's 1, 2, and so it would start right here at time 1, and it would go to 4. So this is 1, 2, right? Once I did that, the only thing left is 2, 2, right? So 2, 2 would start here at 4, and it would go to 7, and that would be my schedule. Okay? And so if I use this rule, I'm guaranteed to have a non-delay schedule. If I use that minimum start time rule, I'm guaranteed to create a non-delay schedule, which I just did right here. Okay, now if I do the other one, I have 2 options. One option is I do the same thing that I do here, because now I have to choose. And once I choose one, the other one, there's only one other one, right? So one option if I do this one is this same schedule, but I have the other option is if I choose 2, 2 first. And if I choose 2, 2 first, this is going to be M1, M2, M3, 1, 1 goes to 1, 2, 1 goes to 2. And now if I chose this one first, okay, it's going to start right here at 2, and it would go to 5. This is 2, 2. And then 8 would be 1, 2. Okay? Which is what they did. Okay? So this one, if I use this rule, it generates a guaranteed non-delay schedule. If I use this rule, then I can potentially generate active schedules. Well, I can generate active but not non-delay schedules, I should say. Okay? Does that make sense? Okay, so in this case, if you think about a make span objective, the non-delay schedule works better, right? Because it finishes at time 7. This one finishes at time 8. So if our objective is make span, in this particular case, the non-delay schedule is better. But suppose my objective is a priority-based objective where part 2 has a higher priority. So for whatever reason, I want part 2 to finish as soon as it can. Well, then this one is going to be optimal. Okay? Further, suppose that I say, let's add a third step on part 2. Okay, if I had a third step on part 2 that has to go back to machine 1, and I do a non-delay schedule, it finishes at 10. But if I do an active schedule, then it's going to finish earlier at time 8. And so in this particular case, the active schedule is optimal for both criteria, make span criteria and non-delay, and priority to job 2 criteria. Okay, so kind of clear there? Yeah?
Non-delay isn't necessarily optimal.
Non-delay, well, it's not optimal in this case.
Right.
Right, because it finishes at time 10, and this one finishes 8, so it's not optimal in this case. And that's the critically important part here. Okay? Yeah?
Still a little bit confused about the definition of active schedules. So I was thinking, like, why aren't the other ones called delay schedules and they are called active schedules? Why do they need an extra word?
Well, because a non-delay schedule is also active. Right? This one anyway is also active. Right?
Right.
So non-delay is a subset of active schedules.
So since both are active, how do we distinctify between them this way? Like, this is counterintuitive.
Well, I mean, a non-delay schedule is one that has no forced idle time. So if you have any schedule that has forced idle time, it is not non-delay. Determining a schedule's active is more complicated and beyond the scope of what we're going to do here. Okay? But this area of interest to us is this time right here. This period of time, right? This is what we called forced idle time. Right? And so if you think about what's happening there, here I am sitting here at time 1, right? And I'm machine 2. If I'm machine 2, what do I see? Well, I see that it's time 1, and I see that I have part 1 waiting for me to process it. Okay? But I don't want to do that. I want to just sit idle. I want to force it to be idle. Okay? And as we'll see, when we use a dispatching-based approach of which simulation-based scheduling is, for the most part, that's extraordinarily difficult to do. It is extraordinarily difficult using a simulation-based scheduling approach to generate a schedule like this because of the way simulation works, right? That it's working in this dispatching environment where I'm saying my dispatching choice is select from among the things that are available. Well, here at time 0 on machine 2, nothing's available. I have nothing to do. At time 1, something becomes available. So from a dispatching rule standpoint, select the best thing available. Well, there's only one, so I select it. That's how I get non-delay schedule. Okay? And so we're going to see that over and over. Okay? What time is it here? Okay. So, as I said, discrete event simulation is a lot like schedule generation. Okay, so if you look, I have this example. I put this on Canvas. I'm pretty sure I put it on Canvas. If I didn't, I will. But it's called schedule generation example. Schedule generation example. And there are two models here. There's a simple model where I just do that same schedule generation. So I have 3 parts, and I have their sequence, and I have all 3 of them arrive. Right? And so when I think about this from a schedule generation standpoint, if I just run my schedule, okay, and fast forward to the end, as we saw, okay, I just generated that schedule, okay? But if I look at this if I look at the trace, okay, so if I go back to my facility view and say, let's run this with the trace on, okay? And so what does the trace do? Well, what the trace does is it prints out the event calendar. Okay, and if you were to look at this event calendar closely, you're going to see something exactly like this happening, right? Because it follows that same general approach where it's basically saying, I've got a whole bunch of things to do. I want to find the earliest time that I can do something, and then I'm going to pick one of those things to do. Then I'm going to update my event calendar, and I'm just going to stay in that loop forever, right? As long as I have something to do, I'm going to figure out when is the soonest I can do something, and then I'm going to do it. Okay, and so that generates, if you look at this, the event calendar, it generates a schedule exactly like we did here. Now, as I said, this one is much more difficult, and we're going to see this. It's practically impossible. Well, practically it is impossible, but it is technically possible to do it. But it's highly impractical. So we're going to do things like this more often than not. Where it gets interesting is where we add more complexity. Okay, we add more complexity. And what we're interested in, I skipped this part last time, was something called an actionable schedule. Okay, and an actionable schedule is something that can be implemented directly. And so if you look at this Gantt chart, right, again, think about this as in a facility where you have an operator for R1 and an operator for R2, and you say, here, you do this. At time 0, you do J1. At time 5, you do J2. At time 11, you do J3. And at R2, you say at time 0, you do J2, then at time 3, you do J3, then at time 5, you do J1. Okay? And if you can do that, I mean, that's what we mean when we say it's actionable, is that, you can implement it. But suppose that in our system, we have setup requirements. Okay, we talked about setups last time. So suppose in this arbitrary system that I created, I have some setups that I have to deal. In other words, when I switch from one part to another, I have to set the machine up. And I have a person that needs to do that setup operation. Okay, I have a setup operator to do that. Okay, so if I have that situation, but I use this model to generate my schedule, the schedule is not actionable. Because depending on what the setup requirements are, I can't start the job at time 0 because I have to set it up. And if I have 2 operations that are supposed to start at the same time, and they both need the operator, I can't start them both at the same time because I have to choose. The setup operator goes here, sets it up, it starts. Setup operator then goes here, sets it up and starts. So it's not actionable, right? So I can have this schedule, but if I have not included the setups, then the schedule's not actionable. Okay? The model that I have here called simple setup implements that setup. okay? Just some arbitrary setup logic that I created where I'm saying, okay, I just added this other column here called setup time. And so for each thing in my sequence, if there's a number there that's non-zero, that's saying, hey, you got to set this up, okay? And in order to set that up, I need this setup operator, right? So if I have to do a setup, then I have to have the setup operator, okay? So my simulation, it's really simple to implement that logic, okay? And note when I run this in my simulation model, if I fast forward to the end and then go look at my planning tab, note I've included my setup operator, and I have all of those situations where I had to do a setup. Okay, they're all included in here. Everywhere on that bottom row where I have setup operator, that J115 is the setup for J115 on R1. The J3 is the setup for J3 on R2, and so on. Okay, so because I've included the logic for the setup operator, my schedule that I've generated is completely actionable. Right? I hand it to the setup operator and say, hey, at time 0, you need to be at R1. Then at time 3, you need to be at R2. And at time 6, you need to be at R1. And time 7, you need to be back at R2. Right? And then I also have the start time for each one of the parts. Okay, so when we talk about actionable schedules, that's what I mean, is that it includes all of the detail required to create a schedule that you can actually implement. Okay? Yeah.
Does Simio include the processing time, or the setup time in the processing time when you make that schedule?
So what happens in Simio, and we're going to do a lot more detail about how setups work inside Simio, but basically what happens in this model is that I have a time here for this if you look at this operation right here, there's a setup time, which is 1 time unit, and from 1 to 8 is the 7 time units for the processing. So what Simio does is it says, okay, I'm going to, at least the implementation I have right here, says I'm going to reserve R1 at time 0, then I'm going to go and grab the operator, then I'm going to do the setup, then I'm going to delay for the processing time. So that orange bar that you see across the top on R1 is the addition of the two, the setup time and there are other ways to do it where you don't have to add them. They can be running concurrently and all that, but this one is a really simple one where I just have them running sequentially. Okay? Okay, so the advantage of using discrete event simulation is I can implement arbitrarily complex constraints. Setups, operators, work schedules, materials, all of those things that complicate, I can include in my model. And once I've included in my model, when I generate that sample path, or I generate the event calendar that we saw, I'm essentially creating a schedule. And if I've included all the details about the operations, what gets generated is an actionable schedule. Okay, so in general, if you compare optimization-based approaches on the left, combinatorial optimization-based approaches are usually under-constrained. I usually ignore things like setups, or I abstract setups away by saying they don't require a second operator, so I'm just going to lengthen the processing times or things like that. All right, so you typically take a complex problem and you make some assumptions so that you make it solvable. Okay? And it makes perfect sense to do this from an optimization perspective because the systems are already complex. So it's already difficult to solve this combinatorial optimization problem, even if I ignore everything. But the result that I can get mathematically optimal solutions to my abstract problem, but they're not actionable. All right, so think back to the example where I don't include setups. I can have an optimal schedule from the operation time perspective, but it's not actionable. I have to make further decisions to have a schedule that I can actually execute. On the other hand, simulation-based scheduling approach implement a dispatching approach. Problem with implementing a dispatching approach is this problem right here, is that I can't generate this schedule using a dispatching approach. So if I give you this problem, said, hey, write me a Simio model that will generate this. Again, technically it can be done, but it's difficult and impossible to do it in a way that would always give you the best solution. I could force it to do this, but the next time I had a similar problem, it wouldn't work. Okay, so when I say it's not practically possible to do it, that's really what I mean. Okay, so simulation won't do this. Okay, so it can implement arbitrarily complex constraints to fit any system, right? I can have any kind of resource constraints, any kind of setups, any kind of work schedules, any of that stuff. Okay, but I can't do things like this. And so we're in with this question. If I have an optimization approach, I'm generally have optimal solutions to an under-constrained problem. I haven't considered setup times, for example. I have the optimal solution by ignoring it, or I can have feasible solutions to the actual problem. Right? So the optimization-based approaches generally will give me an optimal solution to an under-constrained problem, whereas the scheduling approaches give me a feasible solution, okay, to the actual problem. And so where simulation-based scheduling is an attractive alternative is where the optimization approach, it's difficult to take that abstract solution and make it actionable. Right? So if I give you the Gantt chart with the abstract solution and say, okay, now make this actionable, for this one it's easy. Add a setup, add a setup, add a setup, and it's done. In the general sense, it's not easy at all to decide how best to do that. And so in the cases that we're primarily interested in, generating a feasible solution, and hopefully good, not just feasible, hopefully it's a good solution, but not provably optimal, is our focus. Okay? Does that make sense? Okay. Onward we go. That's the whole first slide set. Where's my second one? You only have 2 slides here, so don't worry about this one. We're not going to be here that much longer. So the next thing that we're going to do, that's our complete general introduction to scheduling, by the way. One whole class and one little piece, half of another class. Okay, so we're not interested in optimal scheduling anymore. So if you're interested in the formulation and how we mathematically solve, sorry, we're not going to do that anymore. So we're going to kind of focus on this simulation-based scheduling approach and how to do it, and how to use, in particular, Simio-RPS to solve that problem. Okay, where our objective is to always create actionable schedules. Okay, so over here on the left, it's a general technique. So simulation-based scheduling is in no way tied to Simio-RPS. You can do the same thing with virtually any discrete event simulation package. Okay, Simio-RPS, what it does is it gives you some tools that simplify the process. Okay, simplify the development and use of these types of models. And so in general categories of things, data integration tools, data-driven data modeling tools, enhanced Gantt charting features, and dashboard creation tools. So you can use, you're essentially creating models. Once you create the model, you're generating the event calendar, and then you're taking that event calendar and you're making it useful. Useful in the sense that, I'm going to take this long task list event calendar and create a Gantt chart so that a human can look at that Gantt chart and say, I like this, I don't like this, I want to move this, or whatever. Or you're taking an event calendar and saying, let's look at some generic performance metrics like make span or number of late jobs or things like that. Okay, and so that's what I mean by where you're taking that Simio-RPS provides tools to do that. So what I want to end on today is I want to talk about some general features here, and we're going to demonstrate this. I've already demonstrated a little bit in video module 2. We do a lot more of it in video module 3, so I want to spend our last 15 or so minutes talking about some of the details. Okay, so I'm going to switch to Simio, do this all in Simio here. Which one do I want to do? Modify 3. So here's this is a modified version of the one I did for video module 2, job shops, just modified for C03, so modified for today. Okay, so I want to talk from this. Okay, what I'm going to talk about is this general structure. Okay, now, I mentioned on the video, and I'm going to mention here, and it will still confuse you, I promise you, because it still confuses, a lot of people. There are 3 modes when you run Simio. There's interactive mode, there's experiment mode, there's planning mode. Okay, so if I go to my model, let's go to my arrival table model here, and I'm here in the facility view, and I reset it. Let me reset everything. So I'm going to go reset my plan, my planning. I'm going to reset that guy. I'm going to go to my experiment. I'm going to reset that guy. Everything's reset. I've reset every round, okay? When I talk about running these modes, facility view or interactive mode, okay, when I run in the interactive environment, so I just sort of fast forward there, and it ran to the end, okay, you can think of it keeping track of all of the stuff in one little spot called interactive mode space or something like that. So if I go to my results, there they are. My typical pivot grid results that we see. I have reports, dashboard reports. We've already seen Gantt charts a little bit here. But all of this stuff is existing in interactive mode. Okay? Similarly, what we've seen in Semio classes before is experiment mode. So I go over here to my experiment, and the fact that I ran in interactive mode, there's no results here, because it's a completely different space. Okay, so if I want to have results here, I have to run it here. Okay, so I can run it. I'm not going to let it run all the way. I think it takes a little while. It doesn't take too long. And now when I run in experiment mode, it's storing all of the data in this other space called experiment. We'll call it experiment mode space. Okay? And so when you run in interactive mode, what it does is it says, I'm going to take all of the random components of the model and sample one time, right? And then it stores those values, right? So it's equivalent to sampling once everywhere and then storing those values, okay? When I run in experiment mode, it replicates. So in this case, I have 40 replications. So it's going to run it once where it samples my random numbers. Then it's going to run it again, sampling a different set of random numbers. Then it's going to run it a third time, sampling a different set of random numbers, right? And then it's going to accumulate all of the results across those replications. Okay? Now, I can sort of do that in interactive mode. Probably learned when you were working in learning Semio. If I were to go back and say, let's fast forward again and look at any of my results, they're exactly the same, right? 9.17, because clicking start, reset, start, reset, start, reset is not running multiple replications. It's running the same replication multiple times, because you're not sampling from different random number streams. You guys remember that? Technically, you can. So there is an option here that we use sometimes. If I go up to advanced options, randomness, I can set the replication number. So I could set that replication number to a different replication, and then when I run an interactive, then I am running a different replication. Okay, so I can sort of mimic doing experiment in interactive mode, but it's only storing one thing at a time. Okay, so you should have seen all of that, except maybe the random number stream thing. You should have seen this differentiation between interactive run and experiment run. Now we have this third guy called planning space, which you probably have not seen. And that's a totally different space. Okay? So you see I have nothing here. So I've run an interactive run. I have those results. I ran an experiment, but I don't have anything here in my interactive run. Okay, that's a completely different space. So when I run here and say, okay, I'm going to go to, let's see, I'm going to go to my operational plan, create a plan. Now it essentially ran in this planning mode. Okay? Now, that makes sense? Any questions for me so far? So where planning mode differs from the other two is that there's no randomness in planning mode. Okay, there's no randomness in planning mode. When it samples a value that has a random expression, it replaces it with the expected value. Okay? So again, that's fundamentally different than interactive. Interactive, I end up with one observation, but it's randomly sampled. Planning mode, it takes the expected value every time. Okay? That makes sense? Okay, but what you see in these modes, especially between interactive and planning, the same general look, right? So here's my resource Gantt for planning mode, and I go look at my resource Gantt for interactive mode, and they look pretty similar. But if I look at my entity Gantt here, and I look at my entity Gantt here, they have the same structure, right? They're generated the same basic way, but they're different. One of them is from the interactive run, one's from the planning run. Okay, so back to your question from the beginning, if sometimes you get lost as to where you are, this happens all the time. You're looking at one, you're saying, wait a second, I'm not in planning mode, I'm in interactive mode. Okay, so you have to kind of get used to what we're seeing here. Okay? Okay, so as I said, I just wanted to give a high-level overview of what these values are, or what these things that we're going to look at. We've sort of, seen Gantt charts. We've used them a little bit to talk about scheduling in general, but we really haven't touched the surface of the features that they have in Simio RPS. We're going to spend a long time talking about how to use these. It has a lot of nice features, like, for example, if I go and click on the plus sign here, I can see things like the constrained entities. So basically what that's telling me is I start on P1, 2, and all of those other ones are waiting. Right? So from a dispatching perspective, the model made a selection between all of those things that are waiting and said, I want you to do this one first. Okay? And that's done, in this case, if you go back and look at the data, my arrivals, because all my arrivals happen here at time 0. Right? So all my arrivals happened at time 0. So everything is there at the beginning. So you have this broad selection. If they don't all arrive at time 0, then you're not going to have that many constrained entities, but you can see those. Okay, so we're going to see that. In video 3, we go through a bit of detail for the resource Gantt. The entity Gantt just shows by entity, and then if you pick one of the entities, a good one, you can also see where its constraints are. Right, so it's somehow constrained. So this entity had to go from S1 to S to S3. It was blocked on S2. So you can also get information about, for a particular entity, why it's waiting, what it's waiting for. You can see all of that here. Okay, and so learning how to interpret the information is something we're going to spend a while doing. We also have a whole bunch of logs. So we can think about logs as different ways that we can cut the event calendar. So you take the event calendar and you say, hey, I want all the resource usage information. Every time any resource is used, I want to know what time it started, what the resource was, what time it ended, what the entity was that we used it. So all of that information is here, right? And it's these log files where all of the Gantt charts and all of that come from, okay? We also have something called dashboard reports, which we will see, but we're going to see those probably after the midterm. So dashboard results are just a different way that we can look at the results. So for example, I have a simple one here, and in video 3, there are 2 dashboards we use. We don't build them; you just import them. And it goes through the video how to do that. I think this is one of them. And so what it shows you can go here and look and say, okay, let's look at S1. Looks like S1 was busy about 71% of the time, and it was starved 24% of the time. And here's the dispatching list that you would do, S2, and so on. So what the dashboards give us a way to do is just evaluate this schedule that I generated, right? So if I'm executing in planning mode, I generated a schedule using expected values for all of my random expressions, and here's the schedule that it generated, the make span, and all of that kind of stuff. Okay, so we're going to see logs. We're going to see the dashboard reports. We'll see targets and all of that stuff as we get more into the scheduling thing. But as you watch video 3, again, keep in mind 3 modes: interactive mode, planning mode, experiment mode. The confusion mostly happens between interactive mode and planning mode. Okay, interactive mode uses randomness. Planning mode does not use randomness. Okay, and so you can see in video, I think in video module 3, I think I got rid of all the randomness in the model, actually. I think I just generated, instead of having expressions for the processing times, I think we just generated numbers rather than those expressions. Okay? So, have a look at that. Experiment with these values that you see, or the components that we see, like the resource Gantt, the entity, workflow, the logs, and all of that kind of stuff, because we're going to use those as we get more into the scheduling area. Because in a typical scheduling project, you don't just sit down and build it. You work on it, you evaluate, you work on it, you evaluate, you work on it, evaluate, and a lot of the evaluation is done with these tools. So you're looking and saying, hey, why is this happening? I don't like the fact that, P121 comes before P159. Right, so I want to look at the model and say, okay, why is this happening? And then I might go in the model and make a change and say, okay, let's reprioritize. Let's use a different dispatching rule, or let's set up some kind of structure so that I can use the dispatching rule context, but get the solutions that I want. Okay, and so to do that, you generate a schedule, look at it, try to see what you'd like to have different, and then have to go back and implement that. Okay. I think I covered everything I wanted to cover. I covered almost everything. A couple little things I'll pick up on next week. But with that, I'm going to stop here unless anyone has any questions for me. Okay, video module 3, have a look. Have a look at case study 2 if you have any questions for me. And as always, as I mentioned before, when you're watching the videos, if anything causes confusion, shoot me a quick note, put it on Canvas. I will be happy to review any of those details next time. All right, see you guys later.